time for another round of calculating equilibrium, folks. And this time it's a type 2, the perfect square. We're going to go right into an example because you already know how to set up an ice table, and we're going to see that the setup is the same as a type 1, but how we solve the math is different. So we're going to look at those differences. So carbon monoxide reacts with water in a gas form to produce carbon dioxide and H2 gas. At 900 degrees Celsius, K is 420. Remember I mentioned in that last lesson how K is always put together with a degrees Celsius? That's because K is temperature dependent, which we'll see later on in terms of why. But in terms of actually needing that number, we don't need it, just so we know. So we want to calculate the concentrations of all entities. Sorry, my dog has just come into the closet. All entities if 2.50 moles of each entity are initially placed in a 3-liter closed container. So here is our ice table all set up. We've got our balanced equation along the top, and down the side we have our ICE. Then we're going to go back to our word problem and we're going to read it and see what goes into the I part. Remember, that's the only part we get from the word problem. So going back to it, it says that we are calculating all the entities at equilibrium if 2.5 moles of each entity is placed into a 2-liter container. So we have a little bit of side work. C equals N over V. And we've got 2.50 moles in a 3-liter container. And we'll end up with 0.833 moles per liter. This says that all entities are placed in the container, so a little bit different from the last problem at type 1, we actually have values everywhere. We now get to our next problem, and that is when we do our C value. Normally C's are easy to predict because there's a 0, and you can't have a 0 at equilibrium, so you always shift towards the 0. However, there are no zeros this time, which means we are going to have to use a Q. This is the only time we have to do one of those Q calculations that we learned in our last unit, because this will allow us to figure out which way to shift. So we have a little bit of side work over here. We're going to solve for Q. Remember, Q is the same as K, concentration of products divided by concentration of reactants. The only thing is we can substitute any numbers in there, so I'm going to use my I values into the Q, and we get a value of 1. Now we're going to compare Q to K. So the K was given to us. K was part of the original problem. K is equal to 4.2. So now when I look at how Q compares to K, Q is less than K. And so if I look at my Pac-Man, it's shifting to the right. It's going to gobble to the right. So therefore, I'm going to shift right in my equilibrium. So I'm going to apply that shift back into my ice table now. So shifting to the right means the left side is going to get used up and the right side is going to increase. And the proportion is the ratio that we see according to coefficients. So 1x, 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 1x. As always, E is I plus C. 0.833 minus x. 0.833 minus x. 0.833 plus x. 0.833 plus x. All right, now that we've got this all set up, we are going to solve a little bit differently now. Again, my end goal, of course, is to solve for values at equilibrium, which means I need to figure out what the heck x is. At type 1, I've been given one value at equilibrium, and that's my way for solving for x. This time I'm going to use the fact that I know k to help me solve for x. So we're going to use a k equation to help us solve here. So just like Q, K is equal to products over reactants, so CO2 times the concentration of H2 divided by the concentration of CO times the concentration of H2O. Remember, we can use the H2O here because it's in the gas form, not the liquid form, so that's allowed. Because we're dealing with K, we have to use equilibrium values only. and that means we're going to use the values from the last part of our ice table. So we've got 0.833 plus x for the CO2, 0.833 plus x for the H2, 0.833 minus x for CO, and 0.833 minus x for H2. We can now do a little bit of fine-tuning. K can be replaced with what K is equal to. And on the top, we can actually write this as 0.833 plus x all squared. And on the bottom, we can write it as 0.833 minus x all squared. And this is why this particular type of problem is called a perfect square, because at this point, we can actually square root both sides. So I can take the square root of this side, and I can take the square root of this side. Remember that square rooting on the right just simply means I'm going to get rid of those parts there. And then on the left, we'll actually come up with a legitimate number for that one. So this is why it's called a perfect square. So I've square rooted both sides, and now I need to isolate x, because again, if I know what x is, I can substitute it in the E part of the ice table and solve for things at equilibrium. So I'm going to cross multiply the part on the bottom here. So it'll be 2.05. We're just going to keep our bracket here so you can see the math. This is just math, it's not chemistry. And if there's something outside the bracket, we have to multiply both things inside the bracket. I want you to take your time and solve here. Once you've got all of your pieces, you're going to end up with a numerical term, an x term, a numerical term, and an x term, which means you're going to have to collect like terms. So here we've multiplied things out, and now we're going to do a little bit of rearranging. So 1.71, we'll keep the numbers on the left just to keep them positive, and we'll keep the x's on the right to keep them positive. And then we'll solve on both sides. And last step, we want to divide by 3.05 to get x by itself. So x is equal to 0.287 moles per liter. So the last step then is to figure out what the values are at equilibrium. And because the values are the same as each other, we can write this a little bit sort of grouped together, I guess. So the reactants, the carbon monoxide and water, they're the same. They're 0.833 minus x at equilibrium according to my ice table. So I can group those guys together and then just substitute my x, 0.287, and then come up with my answer, 0.546 moles per liter. I'll remind you here when we're subtracting, it's lowest decimal places. And then we can do the same thing for the product side. Again, I'm going to group them together since they're both the same, and then substitute my x, and then add. And again, I can use lowest decimal places, so I'm going to take it to 3 decimal places, 1.120 moles per liter. And there are my final answers, and that's how it's done. Now, if we wanted to, now that we actually have values at equilibrium, we could do a check if we wanted to. So we could sub these in to K and see if they actually match the K value of 4.2. I'm not going to do that, but that's a really good way to check your math to make sure you've done things correctly. All right, example number 2, we've got I2 gas plus Br2 gas in equilibrium with 2 IBr gas at 500 degrees Celsius. K is 1.2 times 10 to the negative 2. We want to calculate the concentrations of all entities at equilibrium if the concentrations initially are 1.7 moles per liter for all entities. So you can pause here and get this one started all by yourself. So here's our ice table with our setup. We have 1.7 moles per liter of all entities. That's straight out of the question. And because we have no zero, we are going to have to do a Q. Otherwise, we will not be able to figure out which way this shifts. Obviously, what we've seen most of is things shifting to the right, but you get marks for making sure you know exactly which way it shifts, and also sometimes it shifts to the left, so we actually have to be aware of that. So let's do a Q off to the side. So Q and K, remember, are the same formula. It's concentration of products divided by concentration of reactants. Coefficients become exponents. Then we're going to substitute our values in. So Q, when we substitute our values in, is equal to 1. Once again, that's not always going to be the case, but it is the case in the last couple of examples. And now we have to compare it to K. So going back to the problem, K is equal to 1.2 times 10 to the negative 2. So if I look at Q in relationship to K, this time Q is greater than K, which means it's going to shift to the left. And that means up on my ice table, I'm now going to reflect that. So the left side is actually going to get bigger, and the right side is actually going to get smaller. So the equilibrium actually shifts left instead of right. Again, sometimes this happens, which is why we do a Q. So coefficients become our x's, so we have 1x, 1x, 2x, and as always, I plus c makes e. 1.7 plus x, 1.7 plus x, 1.7 minus 2x. Just like before, our next step is going to be making that k. So k is the same as q. It is our IBR squared divided by our I2 and our BR2. The difference between them is that k is always equilibrium values, so those are the values we're putting in, not just any values. So let's substitute in. We've got 1.2 times 10 to the negative 2 as our k. We've got 1.7 times 10. Ooh, let's erase 1.7. Here we go. 1.7 minus 2x all squared at the top. Don't forget that squared. At the bottom, we have 1.7 plus x times 1.7 plus x. So I'm going to go ahead and show that we are going to square that. Once again, because of the outcome at this stage, I can do a perfect square because it's possible to square root both sides. So I'm going to square root a number. You can always square root a number. And I'm going to square root the right, which will allow me to get rid of those squares. Alright, so here we go. We've already square rooted both sides. Again, my next step is to take the stuff off the bottom and bring it across. I bet you thought you'd escaped my terrible handwriting, but haha, it's even worse with a stylus. Poor things. Alright, so there's our math setup. Again, whatever is outside the bracket multiplies by what's inside the bracket. So we've got 0.19 plus 0.11x equal to 1.7 minus 2x. Now we're grouping our like terms, 1.5, 2.11x, and then dividing through by 2.11. So the value I'm getting here is 0.72 moles per liter. So once again, now that I've got this answer, I can sub it in to the E part of the ice table and solve. Ooh, that's some really good handwriting right there. So for the reactants, they're equal to one another, so I'm just going to do it once, 1.7 plus x. So that's going to be our 1.7 plus 0.72. And we're going to bring it down to one decimal place. So whoopsies. Erase. So we're going to bring that to 2.4 moles per liter. The IBR is 1.7 minus 2x, so again we're going to substitute our x value, 0.7, 2, for a final answer of 0.26 moles per liter. Oh, I should have done that in red. I'll just underline it in red instead. Yay, we did it! Happy face! Oh, even more happy faces because it's homework time. So those are the questions to try for type 2. And we'll meet again next week for type 3.